Problem 1.7. Let X be a set and assume that P is an element of X. Show that the collection T, consisting of the empty set and all subsets of X containing P, is a topology on X. This topology is called the particular point topology on X, and we denote it by ppx sub P. Before we dive into the proof, let's try and write down what this topology is in set notation. We are told that it contains the empty set and also all subsets of X containing P. So all U in X such that P is an element of U. So that's what this collection T is. Now to prove that it's a topology, we just have to check the three properties that the open sets of a topology are supposed to satisfy. So the first one is it just has to contain the empty set and X. Well, it clearly contains the empty set from the definition, and it also contains X because X is a subset of itself, which contains P. So how about we just say that the empty set and X are certainly elements of this topology T. Okay, the second property we're supposed to check is that T is closed under finite intersections. So we will assume that we have finitely many open sets in T. And so what does that mean? Well, then either some U sub I is the empty set, right? That could happen. Or if not, then none of them are, in which case they all have to contain P. So, or U sub 1 through U sub n all contain the element P. Okay, well, in the former case, if one of the sets is empty, then that means the intersection of all of them is empty, right? U sub 1 intersect all the way up to U sub n equals the empty set, which we've already noted is an element of T. And in the latter case, where all of the U sub I contain P, their intersection must contain P as well. So I copy the intersection from over here, and we can say that P is an element to the intersection. So once again, the intersection is an element of T. So we're done. We've shown that in either case, the intersection of these finitely many open sets is, again, contained in T. Okay. And for the third property, we're supposed to show that any union of open sets is open. So this time we can assume that we have a collection of, it's supposed to be an alpha, a collection of U sub alpha, and alpha can range over whatever index set we like, because this can be any arbitrary collection of any size. And, well, let's think about a couple cases again. If every U sub alpha equals the empty set, well, then the union is equal to the empty set as well, right? So then the union over all alpha of U sub alpha is also the empty set, and therefore is contained in T. And, well, otherwise, some u sub alpha is not empty. And, well, because it's in T, that means it has to contain P. And if P is in at least one of the u sub alpha, well, then it's in the union. So P is contained in the union over all alpha of u sub alpha. And so that proves that this union of all of the u sub alpha is contained in T. So T is closed under arbitrary unions as well. And that finishes the proof.